You able to see my screen?
Yes, sir.
Okay. So, welcome to the Theory of Computation course. So, this is a second batch I'm doing. So, the first batch was at 3 o'clock, and yeah, so I will be taking the Theory of Computing course for both the batches until midterm. And today's class is going to be a general overview about the course. So the first thing is I will be explaining the CIF, which is defined for this theory of computation course. And then we will be looking at why do we need to study about this theory of computation as a computer scientist, what is the necessity, and what kind of problems it addresses, and what are the outcomes that you will get when you learn the theory of computation course. Okay, so that is what we will be looking at in this course. Okay, so first let me start with the CIF. So here is CIF. So this is a theory of computation course, CIF. Again, go through this course content and the overview. So mainly what we are going to address in this course, there are two things which I will be explaining you in the sequence of this class. Two things which we will be doing here is, just a minute. One is the computability and the complexity. So there are two questions which you will be answering using this theory of computation course. So theory of computation course is a very, very fundamental basic course. As you have seen the name, it's a theory behind the computation. So what are we trying to do here? We are trying to build some abstract models of computation and then trying to answer these two questions. One is the computability and the other one is the complexity. Okay. So what do you mean by computability is what are the computational problems that you can solve using an abstract machine? That is called as the computability. And the complexity is once you are able to solve some problem, what is the time and space required to solve it? Okay, so how much of resources you require, that is a space, and how much of time you require, that is called as a time complexity. Okay, so time complexity, space complexity, and the computability are the three things that we will be looking at, and we will be trying to answer those things using the various abstract machines that we are going to see in this course. Okay, so that is the objective of this course. We will be explaining about the computability and complexity in the next 5 to 10 minutes or so. Right. So once you go through this course completely, you will be able to do these course outcomes. You will be able to explain the various concepts of finite automata, Turing machines, halting problem, and such kind of things. And then you will be able to tell the relationship between the machines, languages, and grammars. Okay. And you will be able to recognize the power and the limitation of a computer. What exactly is the power? What are the problems a computer can solve? What are the set of problems the computer cannot solve? All those questions will be answered through this theory of computation course. And to construct appropriate automata and grammars for any given language, you will be able to construct, given a language, you will be able to construct a specific appropriate automata or grammars and prove that it exactly accepts or generates nothing more and nothing less. Okay, so these are some of the course outcomes that you will be able to do once you go through this course. You can go through it. I will not again read it, so you can go through it. Okay, so let's see the contents of these whole course. So there are Unit 1, Unit 2, and Unit 3, and Unit 4. So there are 4 units. The first unit, which is this, is on finite state automata, which we call it as FSA. Okay. So in finite state automata, we will be looking at various types of finite state automata, that is non-deterministic, deterministic, and non-deterministic with epsilon modes. All these types of automaton we will be looking at, and what is the power of all these finite state automata in all its variants we will be looking at. And then we will be looking at regular expressions. Regular expressions, we will be showing that every regular language can be represented using a regular expression, and for every regular expression, we have a regular language, right? So then we will be looking at another characteristics of this called as a pumping lemma, and then we will have a Michael-Nero theorem, which also gives another characteristics of the finite state of the regular languages and the finite state automata. And then we will be looking at, in the second chapter, we will be looking at the push down automata. So that is called as PDA. PDA and context free grammar, both we will be looking at. Okay. So these two we will be looking at, and we will be defining various versions of push down automata. That is acceptance by empty store, acceptance by final state, and then we will be showing the equivalence between the push down automata and context free grammar. We will be showing the power of both the push down automata and the context free grammar is one and the same, right? And then we will be looking at some of the normal forms of context free grammar. We have Chomsky normal form, we have Grayback normal form. All those normal forms will be defined here, and these normal forms are very, very very important, because it has a lot of applications, especially in the natural language processing, which I took the last semester. So these normal forms are very helpful for parsing algorithms and all. And then we will be looking at the third chapter. We will be looking at the Turing machines, which is a complete abstract machine for any computer. So if you think about a computer, and if you want to have an equivalent abstract machine for that, and then the Turing machine is the one which is equivalent to the computer that we know, right? So the Turing machine, as you know, it is first proposed by Alan Turing way back in 1930s and 40s, right? And it is still the abstract model which acts as the precursor for building a computer, right? So whatever that we are using right now, okay? And then we will be looking at various versions of Turing machine, that is the generalized and restricted version. And then we will be looking at universal Turing machine. So that is a programmable Turing machine, how to do that. And then we will be looking at the time-space complexity measures also in the last section of this chapter. And then in the fourth unit, we will be looking at various problems like the decidability, and then the membership problems, emptiness problems, equivalence problems we will be looking at. And then we will be looking at the time and state complexity measures of the Turing machine. And then we will be defining various classes like P and NP completeness. And then the satisfiability problem we will be looking at, and some of the NP complete problems also we will be looking at. So these are some of the things that we will be looking at in this course. Okay, and these are the reference books. The Introduction to Automata Theory, which is the first one, by Hopcroft, Motwani, and Woolman is the most popular book for automata theory, and I'm going to refer to this main. So this is my main book actually, and these two are will be supporting books actually. Okay, so this the second one is by Papadimitriou. This is also a very good book, and the Peter Lynch, that is the third one, contains a lot of solved problems. If you want to have a look at the solved examples, I think Peter Lynch will be the best book to refer to. Okay, so these are the three books which we will be referring for this course. And then there are some additional resources if you want to have a look at some NPTEL videos. You can have a look at this link which I have already given. This is from IIT Madras and Professor Kamala Krithivasan's course, which is on the theory of computation. Is there like 40 lectures are there available? You can have a look at it if you want to have further additional knowledge on the theory of computation. And of course, Professor Kamala Krithivasan was my PhD advisor also. So whatever that I teach, I owe to her actually. And she is one of the best teachers and one of the greatest researchers in theory of computation. So, so you can also refer to this NPTEL video, right? So then the most important thing, that is evaluation method. So we will have two quizzes, quiz 1 and quiz 2. One before midterm, one after midterm, and then we will have assignment also, which I'm not very clear if we will be having assignment or not. So assignment will be of 10%. Most probably it will be having only 2 or 3 assignments. But if the assignment is not there, we have decided the assignment is not there, then that 10% will be equally distributed to the midterm and the final exam. So midterm will become 30 and then final exam will become 50, right? So if assignments are not there, okay? So that I will tell you after getting the confirmation on Wednesday, okay? So these are the components of evaluation and the contents of this course, which we will be looking at for this semester. And if you have any doubt on the CIF and the course contents, please let me know. I will give you a few minutes. I will go back to the chat window and then look for any questions if you want to ask. Class recordings will be uploaded in the Piazza classroom, which I will be using for all kinds of communications and the sharing of resources. Okay, so the class recordings will be the links will be given in Piazza classroom. You can have a look at it every day. No, not every day. I mean, whenever the class is there, all those classes will be recorded and then it will be put there in the Piazza classroom. And there will be a separate thread I will be opening, and there, so that thread will be having all the links, so you can refer to any of the recordings at any point of time. Okay, so there is no problem in that. And for the course communication and sharing of resources, I will be using Piazza, not Google Classroom. Okay, so I will not be using Google Classroom. I am using Piazza for all communications. Everything will be through Piazza. But the exams, that is a quiz and the midterm, everything will be conducted using Moodle. If at all everything is going to be online, it is going to be through Moodle only. Okay. Any questions you have? I'll give you 1 or 2 minutes. Okay, so if we don't have any questions, let me start. We'll go back to the theory of computation, what we are going to look at in this course. So we will be giving a very overall view about what exactly is this course about and what is the motivation to look into this theory of computation. What is the necessity for a computer scientist to know about the theory, right? So that is very important to look into it. This is one of the very few theory courses which is still remaining for a computer scientist, right? So let's see what is there in this course and why do we need to study about this course, right? So let me start with what do you mean by an algorithm? What do you mean by an algorithm? So it starts with, so you will be going through side by side, I think, design analysis of algorithm also, I think, right? So if the algorithm is going to be defined, we will be getting a prefix like this, a sequence of computational steps. So algorithm is nothing but a sequence of computational steps. So it is not only steps, there is an adjective which says that it is a computational step. So what do you mean by computation here? So the computation is the one which relates this to the computer science, right? So we are all computer science engineers, right? So you need to know what do you mean by computation here. So what are the computations? It is not only the arithmetic operations that we are going to do here. So the calculator does all these arithmetical operations wherever you want, right? It can square some numbers, it can multiply some two numbers, it can add some numbers, it can subtract, whatever, right? So all those operations are possible in a calculator, but the calculator cannot be programmed. It cannot do much beyond the operations like the addition, subtraction, division, and all, right? So a computer has more flexibility than a calculator, because one of the main difference in the computer is it can be programmed, and the same thing can be executed automatically by the computer, right? So in a calculator, you may have to press every time. If you want to calculate 2 plus 3, you need to press 2 plus 3 again and again, right? But you can program in a computer. The 2 plus 3 can be programmed, and if you want to calculate the addition, you can just call that function or a program, whatever, right? So computer is a much more beyond than a calculator, right? So it has a computational steps. What are those computational steps? It can have a decision kind of a statement, like if then else kind of statement, which you would have gone through in the computer programming course. And it can also have some kind of arithmetical operations, binary operations. It can do, right? And another main point is it can do the iterative process also. For I is equal to 1 to 100, you can do some of the steps which is inside the loop, right? So all these things constitute a computation, right? So these are the steps which we can do as a computational steps when you are writing a program or when you are writing an algorithm, all right? So every step is going to be some kind of a decision step, or it's going to be an assignment step, or is it going to be some operation that is going to be performed, and then it might be an iterative step, right? So all these things are possible. So when I'm going to look at these steps as a computational steps, now I'm going to look at, if I do these kind of computational steps, what are the problems that I can solve? What are the problems that I can solve, right? So that is a very basic question. If you can go back to the era of maybe 1950s, before this electronic computers and all came into picture, right? 50s and 60s and 70s, right? So if you are in that era, we were not having a computer also in front of our eyes, right? People were thinking of finding some kind of a device, right, that can automate the process, that can do some of the computational things which a human being cannot do more efficiently, right? So a human being can do some kind of a planning kind of a thing, which a computer cannot do. But if it comes to a computational step, like multiplying a 5-digit number by a 7-digit number, or adding maybe a 100-digit number or something like that, the computer can do it in a very efficient way than a human being, right? So people are thinking about, can we build a machine using using these kind of computational steps, right? So if that is the case, if I want to look at the problems that needs to be solved by these computational steps, the natural question that arises in you is, what are the set of problems that computer can solve, if at all a computer is built, right? So if at all a computer is built, what are the problems it can solve? What are the problems it cannot solve, right? So there we are coming to picture. So suppose I denote the set of all problems like this square. Then I want to find the set of problems which is solvable in nature and the set of problems which are unsolvable in nature. Okay, and that is called as a computability. Computability means what are the problems that is solvable and what are the problems that are unsolvable. Computability. That is the main core part of looking at the theory of computation. It answers what are the problems which are solvable, what are the problems which are unsolvable. And the complexity part comes into picture when we are looking at the solvable problems, how efficient you can solve. That is called as a complexity. And according to the complexity, we can define several classes of problems. One is called as a P class problem. The other one is called as a NP class problem. There are some problems which are called as NP complete problem. There are some problems which are called as NP hard problems. Okay, so P for the sake of completeness, it is a polynomial time running algorithm is there, right? And NP means it is non-deterministic polynomial. It is not non-polynomial. Okay, so just try to get this. Many people have already taken it as like non-polynomial. It is not non-polynomial. It is non-deterministic polynomial. In a non-deterministic machine, in polynomial time, you will be able to solve that problem, right? So that is the thing. So we will be coming into these classes in the later part of this course. I'm just giving an overall picture, okay? So I'm not going to define anything P and P, what do you mean by? As of now, we don't have the enough resources to define those classes, okay? So we will be taking that in the last part of this course. That is the third and the fourth unit. That is after the midterm, okay? So the main point of looking at the theory of computation is to address these two questions. What is the computability and what is the complexity? Computability addresses the question about what are the problems which are solvable in nature, what are the problems which are unsolvable in nature. Complexity addresses the issue like, if it is solvable, if the problem is solvable, how efficient you can solve. We will say that if the problem is in P class, we will say that those problems are efficiently solvable. If it is in NP, we will say that it is solvable, but it takes exponential number of time. So that is the main thing. Okay. So we will go into the much detail of all these things in the later part of this course. But when we are looking at this solvability, that is a computability, we will be looking at various kinds of abstract machines. The abstract machines are of two types. One is called as the automaton, and the other one is called as a grammar. Okay. So in the next part of this class, we will be looking at what are the types of automaton that we will be looking at, and what are the types of grammars that we will be looking at. Okay. So let me stop for a few minutes and see if there are any questions until this point of time. So let me go back to the chat window. So if you have any questions, please let me know. Okay, so there are no questions. So let me go back to the screen. Right. So what are the things that we are going to look at? So let me go to the one screen and then try to explain what are we going to see here. So there are two kinds of abstract machines we will be building. One is called as the automaton model. Automaton, and the other one is called as a grammar. So these are the two things that we will be looking at. The automaton is called as accepting devices. Why we call it as accepting devices, we will be explaining it in the later part of this course. Okay, and this is called as a generative devices. So these are the two abstract types of machines that we will be looking at. Okay, automaton and grammars. Automaton are accepting devices and grammars are generative devices. Okay, in automaton, we will be looking at four types of automaton. One is called as a finite state automaton. Second is called as push down automaton. The third one is called as a linear bounded automaton. And fourth one is called as the Turing machine. Okay. And then in grammars, we will be looking at again four types. One is regular grammar. Second is context-free grammar. Third is context-sensitive. Context-sensitive grammar. And fourth is type 0 grammar. So in the whole course, we will be looking at these four types of automaton and four types of grammar and some variants of this. There will be some variants of finite state automaton, which is like deterministic finite state automaton, non-deterministic finite state automaton. Like in push down grammar, we will be looking at again deterministic and non-deterministic. So like that, there are variants, but mainly these are the main topics that we will be looking at when I am talking about an abstract machine. So this is one type of abstract machine, which is called as the accepting device, and the other type of abstract machine is the generative device. Okay. So why we call it a generative device and accepting devices, we will be looking at in the next sequence of classes. Okay, so that will come through when we define how this automaton works and how the grammars work. It will be inherently, you will be able to get why we call it as accepting devices and why we call the grammars as the generative devices. Okay, so when we are looking at these two types of abstract devices, one is the automaton and the other one is the grammar. The other thing that we will be looking at is the equivalence between this automaton and the grammars. Okay, so we will also be looking at the power of finite state automata and the power of the regular grammar is one and the same. It is same, is equal. Push down automaton and the context free grammar, their power is the same, one and the same. A linear bounded automaton and the context sensitive is one and the same. And Turing machine and the type 0 grammar is one and the same. That's a very elegant kind of equivalence that we have got here, right? So we have 4 automaton devices and 4 grammars actually, and then each of the automaton corresponds to the appropriate one in the type in the grammar actually, right? So finite state automaton is equal to the power of finite state automaton is equal to the power of regular grammar, and so on so in the second and third and fourth types of push down automaton, linear bounded automaton, and Turing machine also. Okay, so when we look at the grammars, first the grammars was defined in linguistics area, that is done by Chomsky. So Chomsky is a linguistic, and he's an American actually. He's also well known for cognitive science and psychology, and he is also well known as a leftist kind of a person, right? So he is already 92. He is living in US, and he has done enormous work in this linguistic topics. So actually all these grammars were defined in the linguistics. In 1957 or so. So way back in 1957. So it is already like 63 years old. So that is what the topic that we are looking at. It's very old topic, but it constitutes the basics of computer science. Okay, so the Turing machine, as you know about from the name itself, it was first proposed by Alan Turing. He's British in I think 1930s and 40s. I think I don't know the exact year. It's around Turing is spelling Turing. So in 1930 to 40, right? So his way of looking at abstract device, then he was looking at addressing these problems like what are the problems that can be solved by a computer. So he wanted to define an abstract machine, and then using that abstract machine, he wanted to check what is the limit of computation. So the theory of computation addresses the most important issue, that is the limits of computing. What is the limit of computing? What do you mean by limit? It gives a boundary that these are the set of problems which can be solved. These are the set of problems which cannot be solved. That is the limit it is giving. And this what is one of the best, and it was the one of the strong basics for the computer science to grow from then onwards. Okay, so Alan Turing is one of the father of computer science, we can say. Right. So in the course, what are we going to look at is we are going to look at the automaton as an accepting devices. We will be looking at all these 4 types, and then we will be characterizing what is the language accepted by the finite state automaton, what is the language accepted by the push-down automaton, what is the language accepted by the linear bounded automaton, and what is the language accepted by the Turing machine. So that is what we will be looking at. And when I talk about the languages accepted by the finite state automaton, it means the power of the finite state automaton. Okay, so what is the power of the finite state automaton? What is the power of the push-down automaton? When I say the power of the automaton, it means that what is the set of languages it accepts and what is the set of languages it doesn't accept, right? So, so when I'm looking at the Turing machine is thought as the abstract machine, which is equivalent to a computer that we have right now. Okay, so when I'm looking at a Turing machine, it means I'm looking at a computer. What can be computed in a computer? What can be computed in a computer can be computed in a Turing machine also, and what can be computed in a Turing machine can be computed in a computer also, and that is the Turing hypothesis, which says, and nobody has able to disprove it as of now. Okay, so whatever can be computed in a computer can be computed using a Turing machine, and what can be computed in a Turing machine can be computed in a computer. So whenever we want to check what are the problems that can be solvable by any computer, we can find what is the set of problems that is solvable in a Turing machine is equivalent to what is the set of problems that is solvable by a computer, right? So that is the beauty of getting an abstract machine. Now, when you are building an abstract machine, you don't have to look at the specificity. The specificity is when I'm looking at a computer now, it is a silicon-based computer. It has some electronic parts inside in it. There is a transistor. There are some integrated circuits which are joining the electronic components and then doing some operations, gate operations, OR gate, NOR gate, whatever the gate it may be. So it is a silicon-based computer. But in future, we may be able to get another type of computers also. It doesn't need to have to be only silicon-based. It can be DNA-based computers. You can have a look at in Google. Try to look for DNA-based computers, DNA computers. DNA is nothing but the deoxyribonucleic acid. You would have learned in biology, right? So using the DNA, how to do these computations, and that is the study of the DNA-based computing. So there is a separate area called DNA computing actually, and there is quantum computers. So that computer uses the quantum quantum phenomena that is existing in the world, right? So it's more of physics now. So it can be anything. The computing paradigm can be anything. So we are fortunate that we are now having silicon computers, but in future you may be getting any other types of computing paradigm. But the study that we are going to look at as an abstract mission should not have the specificity. It should be an abstract mission which is devoid of all the specificity. That is the beauty of looking at the abstract mission. So if I can show using a Turing machine, these are the set of problems which can be solvable by a Turing machine, and these are the problems which can be not solvable by a Turing machine, then that is equivalent to saying to any types of computers. It will be equivalent to a quantum computer. It can be equivalent to a DNA computer. It can be equal to any other types of computers that might be coming into the world in the future, right? So when I'm going to look at the Turing machine or the linear bounded automata or the push-down automaton or the finite state automaton, we call those machines as abstract machines. Why do we call that as an abstract mission? Because we are not going to look into the implementation details. What we are going to look at is the abstract model, and then using those abstract model, we will be checking what is the type of resources that you require, what is the amount of resources you require, and what is the time complexity that you will be requiring, and whether it is solvable or not solvable. Okay. Again, we are trying to address those two questions, which is the computability and the complexity. using this four models. Okay. So whatever that I have said for automaton also holds good for the grammars also, because finite state automaton is equivalent to a regular grammar, push down automaton is equivalent to a context free grammar in a different sense, right? One perspective is an accepting device, the other perspective is a generative device, right? So whenever we are looking at the abstract machine, uh, so what we are going to look at is these two questions. What is the computability and what is the complexity? So we are trying to solve these two questions when we are looking at the theory of computation. Okay, so in the theory of computation, these are the two core things that we will be looking at. One is the computability and the other one is the complexity. Okay, so let me stop here for today's class. Okay, so I will be staying here for a few more minutes, and in the next class, we will be starting with the finite state automata definition and then examples and all. So until this point, if you have any doubt that you need to clarify, please let me know. I will go back to the chat window. So if you have any questions, please let me know. It accepts strings, accepts languages. Set of all strings are the languages. Okay. So we will be coming into that details in the next class. How much string, how much of the patterns of strings it can accept is generally called as a power. So when we define these automata, it will become clearer. A Turing machine is again an abstract machine. It's an abstract machine which is equivalent to a computer. So using a Turing machine also you can solve problems. But there is no physical device which is existing as a Turing machine. Turing machine is an abstract machine. What is equivalent to a Turing machine is the computer that we already have. A machine which is devoid of all the specificity is called abstract. Or you can say that it is a mathematical model. Abstract machine is nothing but a mathematical model of a machine. Does the problem being non-computable means that it is impossible to solve? Yes. There are many problems which are impossible to solve. What kind of specificity? Specificity is the one which I'm looking at, the electronic components, transistors, integrated circuits, for DNA molecules, for quantum phenomena, qubits, right? We are not going to look at the specificity. We are looking at a very generic kind of a model, which will be clear in the next class. Is suffix automaton related to this? I don't know anything about suffix automaton. I don't know. What do you mean by suffix automaton? I don't know. There are various types of automata. So it might be one of the type I don't know. Okay, so we shall meet on Wednesday for the next topic. Okay. So thank you. Bye bye. How come Turing machine has no specificity? Because it's an abstract machine, right? So we will be talking about some symbol, some tape, right? How the implementation is done, how the head is going to go through one cell at a time. That and all the implementation we will not be looking at. We will be looking at the head is reading one symbol at a time. That is a model that we will be looking at. Meaning it can solve anything. So it is an abstract device to solve problems. So once we define about these finite state automata, push down automata, and Turing machine, you will come to know about this. With the first class, it is very difficult to get some kind of an understanding of this. These answers you will be getting in the next sequence of classes. Okay. Good. Okay, so we'll meet on Wednesday at the scheduled time. Bye, all of you. Thank you.